So in this synthesis question, we are using propene as our sole source of carbons. That means that all 6 carbons in this product have to come from 1 or more equivalents of propene, which of course means we're going to need 2 of these because they have 3 carbons each. And the best way to approach this one, when we look at our product, we want to notice that it's an ether. And so we think about how do we make that ether functional group? And what is the best way to make an ether?
An acid?
We can dimerize a primary alcohol to using acid to make an ether. But that only works if we're going to want if we want a symmetric ether. So we could make dipropyl ether, but we want to make a mixed ether here, so isopropyl ether. What else can we do? This one named after somebody. Go ahead.
Well, I was going to ask you, sir, what happened if for the alkene we use CH3 and sodium hydroxide?
If we use, sorry, CH3?
BH3 or THF?
Yes. So if we, one thing to think about, of course, is what can we do with our starting materials? One of the things that we could do with propene would be to add B2H6 followed by, or BH3, followed by peroxide and base. That would give us the anti-Markovnikov addition product. Let's come back to this idea, though, of the making the ether. In general, if we were going to combine 2 molecules to make that ether, what should they be? This is the Williamson ether synthesis. And we can think about this as a question in and of itself. What combination of alkyl halide and alkoxide would make this ether? Alkyl halide, so 1 piece with a leaving group. Alkoxide, right? Alkyl, and then oxide, so oxygen anion. If we look at our ether, we think about it retrosynthetically, right? That oxygen had to have been with one side or the other. We want the side that has the leaving group to be primary. So we want the oxygen to have been with the side that's, if there is a side, that's not primary. So we would want this oxyanion, let's just pair it with a sodium so that we have a counterion. And we would want to combine that then with our 3-carbon fragment with a leaving group with, like, let's say a Br. If we don't, if we use a leaving group that's not primary with a strong base, we say strong bases favor what?
Elimination.
Elimination, unless
Methyl or primary.
Exactly, group is methyl or primary. So we need this primary leaving group so that we avoid an elimination reaction. So how would we make these 2 fragments? The hydroboration oxidation puts a functional group at the end of the chain, right? That's anti-Markovnikov addition. Can we convert that to a Br?
HBr?
We can use HBr. We can use PBr3. Either one of those will work great. And there's actually, if we wanted to take a little bit of a shortcut, we could go straight from the alkene to that bromide. Anybody remember how do we do the anti-Markovnikov addition of HBr across a double bond? We use HBr and we add some peroxide. Now, either of those routes works as long as we get this. It doesn't matter if we do it in one step or in two. Then the last thing that we need to do is to create our oxygen anion. We're going to need 2 steps for that. And the first step is going to be to get the oxygen on that center carbon to begin with. So if we can make this alcohol, then we can use either sodium metal or sodium hydroxide or even sodium hydride. Some fancy ways to do it in lab, but if you just put NaOH here, that's fine. From the alcohol, we deprotonate the alcohol or take that hydrogen away. How do we do the Markovnikov equivalent or Markovnikov addition of water across an alkene? This is where we use water and sulfuric acid.